Thanks for joining us on our presentation of our visualization query language that provides a declarative alternative to generating visualization. My name is Nicholas Del Rio of the CyberShare Center here at the University of Texas at El Paso. For further information regarding this technology, please refer to trust.utep.edu/VisKo. This presentation is aimed at helping users understand the notion and purpose of visualization queries, understand why writing queries may be easier than writing traditional procedural pipeline code, and finally learn the visualization query syntax and general procedure for writing queries. The premise of our work is that users naturally think of visualization generation in terms of declarative requests. That is, what visualization they want, as opposed to thinking about how to generate visualizations using some programming language. For example, consider the request. Visualize my seismic velocity data as a set of 35 isosurfaces. In this case, the user declares what view they want their seismic velocity projected as, isosurfaces, as well as specifying that the visualization should consist of 35 of them. Notice how the request makes no mention about how to generate these surfaces. The image shown below is a visualization that satisfies the request presented above. However, toolkits such as the Visualization Toolkit cannot process such requests. Visualization toolkits are software suites that support common visualization functions or operators, such as filtering, gridding, mapping, and rendering. Users are expected to develop custom visualization applications on top of these toolkit operators. More specifically, users are required to construct what are known as visualization pipelines as shown below. This pipeline Java code is based on VTK operators and is able to transform our seismic velocity data into the isosurfaces visualization that satisfies the request presented in the previous slide. In general, visualization pipelines consist of data flowing through different combinations of operator sequences, as denoted with the arrows connecting different operators 1 through 7, indicated by the circles. Each pipeline operator serves a specific role in the transformation process as a whole. In this example, operator 1 ingests the raw seismic velocity data into a form that can be processed by the other operators. Operator 2 extracts the isosurface polygons from the data. The other operators are responsible for adding a bounding box, rendering the polygons, and writing the pixel data to the isosurface's JPEG, as shown in operator 7. In order for users to use visualization toolkits, they must learn to translate their requests into procedural pipeline code. Thus, their declarative specifications must be translated to a more algorithmic specification using an imperative language, such as Java. Users thusly are required to understand what pipeline operators generate the requested visualization, how to transform datasets into forms that can be ingested by the identified pipeline operators, how to transform visualizations into forms that can be ingested by some viewer, which is some application that presents the visualization to the screen, and finally, how to set parameters that control some visual properties, for example, the opacity or color perhaps. We believe users think in terms of these requests, and therefore writing procedural pipeline code may not be intuitive. Our aim is to alleviate users from having to write visualization pipelines and have them write visualization queries instead. A visualization query is a visualization request in some machine-readable form. The velocity isosurfaces request presented in slide 2 can be represented as the following visualization query. This query is segmented into 3 parts to highlight its structure. The first segment selects what view the user wants their data projected as, and what viewer they want to use to present this visualization on the screen, in this case isosurfaces and Mozilla Firefox respectively. The second segment specifies properties about the input data set, such as where the data is located and its type and format. In this case, the velocity data is located at the specified URL and encoded as a binary float array. The final segment specifies any parameter bindings that are used to control properties of the selected view. In this case, the isosurfaces view should consist of 35 surfaces and be rotated 104 degrees about the x-axis. In general, visualization queries follow the pattern below. Brackets indicate an optional clause. Curly brackets indicate a clause that can repeat 0 or many times. And the pipe symbol located within parentheses denotes an option. Provided the rules defined above, the pattern then reads, Select a view URI or wildcard that should be presented using an optional viewer specified by viewer URI. Note the asterisk that denotes a wildcard or any view, requesting that the answering system should return any views it knows how to generate. Carrying on with the pattern, we find the input data characterization clauses, which read, from data located at some URL, which is encoded in a format specified by format URI, and of an optional type specified by type URI. And finally, the parameter segment, which reads, where optionally, some set of parameters are equal to some values. The entities views, viewers, formats, types, and parameters that were referenced by our velocity query example are actually shorthand labels. In practice, all entities specified in a query are referenced by some URI, as was indicated in the previous slide presenting the query template pattern. In our velocity query example, the entities isosurfaces, Firefox, binary float array, velocity, X rotation, and number of contours each have a unique URI, and it is these URIs that we would stuff in the query in place of the labels. Please note that you must have access to a listing of entity URIs in order to construct an executable visualization query. Otherwise, our query answering system will not know the meaning of the query entities. We will show you where these URIs can be found in later slides. In general, writing visualization queries requires a four-step process. First, we must formulate a visualization request, possibly in natural language. Next, we identify visualization query entities from the visualization request in step 1. We then map identified visualization query entities in step 2 to their URIs. And finally, we fill in the blanks of the visualization query template using the entity URIs gathered in step 3. The remainder of the slides in this presentation exercise this four-step process on an example for generating a gravity raster map. The first step in our query writing process is to formulate a request. Guided by our visualization query template, visualization query users, at the very least, need to know about the structure of their data. For example, the format of the source dataset, i.e. the data to be visualized, and the URL where the dataset can be located. Users can further restrict the set of possible visualizations returned by specifying an optional view they want their data projected in, for example isosurfaces, although they can use the wildcard asterisk instead. They need to also specify the optional viewer they want to use to present the visualization. And finally, the optional type of their input dataset. Thus, an example visualization request could read as, visualize my gravity dataset encoded as a table of ASCII characters as a raster map that I can view using Mozilla Firefox. My gravity dataset is located at rio.cs.utep.edu, CI server, CI projects, gravity map providence, gravity dataset.txt. Next, we need to identify the query entities from the request so that we can later map them to URIs. In our running example request, we find that the type of our dataset is a velocity, the format of our dataset is table of ASCII characters, the view our data is to be visualized as is a raster map, the view used to present the raster map is Mozilla Firefox, and finally the data is located at rio.cs.utep.edu, CI server, CI projects, gravity map providence, gravity dataset.txt. We next need to map these identified query entities to their corresponding URIs. A visualization knowledge base is responsible for housing the URIs corresponding to views, viewers, formats, and data types, essentially all the query entities. This knowledge base can provide listings of these URIs along with their labels, for example, the listing of known views as shown in this slide. Given URI tables from the knowledge base, and the query entity labels identified in the previous slide, we can now perform the mappings. The method is to match a label of some identified entity with the label of some URI. In this example, we see that the raster map entity has a URI of rio.cs.utep.edu, CI server, CI projects, VisKo, raster.owl, #raster. We can append a new column to our identified query entity table to house these URIs. We can then repeat this process for the other query entities, such as the viewer. We simply look up the viewer table URIs and find the viewer URI corresponding to Mozilla Firefox, and add that URI in our identified entity table. We repeat this process for the other query entities, format and type. Once we have mapped our query entities to URIs, we can formulate our executable visualization query by simply replacing the query stubs of our query pattern with the corresponding URIs. In our running example, we would replace view with the URI for our raster map. Additionally, we would replace viewer with the URI for Mozilla Firefox. We repeat this replacement process for the other query stubs until we have a valid query. This query can now be executed using the VisKo answering system. To see how to execute visualization queries, please check out our demo on using visualization queries to generate different visualizations for a velocity dataset. This demo can be found on our VisKo webpage located at trust.utep.edu/VisKo. Thank you for listening.